Great. Let's continue talking about sequences then. Sequences. We do have homework due tomorrow. I hope you've had a chance to check it out. About arc length and then some fairly simple sequences questions. We're going to talk a little more, we're going to do a little more interesting stuff concerning sequences today. So like for example, the quiz questions or the test questions about sequences, they may not just be like the ones that are on the homework for tomorrow, but there could be more, fancier stuff about sequences that we're going to talk about today. Maybe just to refresh our memory, or this is an example that I talked about at the very end last time, -1 to the n over n. Remember, the effect of the minus 1 to the n is to alternate the signs. And this is a little, just to remember, n typically starts at 1. So if you look in our book, n starts at 1 unless it says otherwise. When you just write a sequence like this, by itself, this is kind of ambiguous whether it starts at 1 or 0, although actually you can tell on this one it has to start at 1 because 0 wouldn't make sense to plug into the denominator. But anyway, in our book, they always start their sequences at 1. Anyway, what is that? Does it converge or not? If you look at a graph of that, if I were to graph the sequence, which I'm going to do fairly often, the first term is, when I use n equals 1, it says -1 over 1. So that would be here. The next term would say 1 over 2, which is a half. And if you plug in values, the sequence does something like this. And so you can tell on the picture, it looks like this sequence, if I call it an, looks like the lim n goes to infinity of an equals 0. But if you want to actually prove that, it's not so easy to just use the formula because it has this -1 to the n, which is difficult to handle if you think of this as a continuous function. This -1 to the n doesn't really work as a continuous function. So to show that the lim n goes to infinity an equals 0, it's easiest, this example we talked about right at the end, whenever our last class was. It's easiest to show that lim n goes to infinity, absolute value an equals 0. This is a little trick where if your sequence has alternating signs, it is usually easier to show that the absolute value goes to 0. And if it's true that the absolute value goes to 0, that means that the original sequence also goes to 0, because the only way the absolute values of these could approach 0 would be if the numbers themselves approached 0. And this is a lot easier because in this case, so here we have lim n goes to infinity, absolute value an is, this would be lim n goes to infinity, absolute value -1 to the n over n. And what is this when you sort of simplify out the absolute values? What do you say?
1 to the n over n.
Yeah, -1 to the n is the same as 1 to the n when you do absolute values. And what is 1 to the n?
1.
Just 1, yeah. So I think all of this is really just like that, right? Because what you see up top here is a sign. It's either +1 or -1. But in any case, when I take the absolute value of it, you just get 1 every time. And on the bottom, do I need to do absolute value of n down here? Any thoughts about that? They're saying no. Why? I'm just saying n rather than, shouldn't it be absolute value n? Anyone have thoughts about that? Yeah?
If it starts at 1, then you don't really need to.
Yeah, right. And in this case, ordinarily, like if this were x, a real number, you would need to say absolute value x on the bottom. But here, in the context of a sequence, n is a number starting with 1 and then 2 and then 3. So n is automatically positive, and so there's no need to put the absolute values. But anyway, what's this limit? It is 0. Because everybody knows limit of 1 over n is 0. All right. N is always positive. Okay, so this is just a little refresher from the very end last time. We talked last time about a bunch of different rules for limits. I have just one last limit rule. And I would say this one also generally fits in the category of, like, all the rules last time were things that you more or less automatically do without really thinking about them. So this is not a rule that you need to memorize because we're going to just sort of naturally do it all the time. But what it says is if f is, I'll say f of x, is a continuous function, so I'm talking about sequences, but how does a sequence interact with a continuous function? If f of x is a continuous function and lim of the sequence, n goes to infinity, an exists, then here's the real deal. If I have a limit of f of an, this is the same as f of lim an. This is somewhat weird, but I mean, it's weird looking on the paper. But actually, like I said before, this is something that you will naturally do without even thinking about it. Even though it looks weird, it actually is a very natural property. It says if you have a continuous function and the limit of the sequence exists, you can sort of push the lim through a continuous function. That's what this means. This is strange but true fact. Why do I say, like, you've been doing this all along? Like, for example, typical way that you would use this. What is lim n goes to infinity of, for instance, cosine 1 over n? Now, how I would do this, even like without thinking about anything, I would say, okay, I'm doing the lim as n goes to infinity. 1 over n, when the n is really big, becomes like 0, right? When n goes to infinity, this becomes something like, you could imagine 1 over infinity, but that's 0. And then I would do cosine of 0, and I get 1. So the answer I would expect to be 1. Actually, in order to write out the details of that, it requires this step. So what I was thinking is, the cosine here I don't really care about. All I care about is the limit on the inside here. So this, to write out in steps, this is exactly how I was thinking about it in my head, even if you didn't really think in exactly these terms. It is what I was thinking. 1 over n, when n goes to infinity, becomes like 0. And the answer is 1, all right? So the rule that you see in the box here, it just means if you have 1 over n inside of a cosine, that you can kind of temporarily ignore the cosine part and just look at the 1 over n part and take the limit of that part. All right, this is the last of our limit rules. You can do a limit inside of a continuous function. It has to be continuous. If the function is discontinuous, then weird things can happen, but continuous function, it's all good. All right, any thoughts about that? That was just one leftover, somewhat obscure. I mean, it's weird looking, but like I said, you actually use this rule all the time, kind of usually in your head. All right, great. Let's talk about a specific type of sequence that is going to be a sort of standard example for a lot of what we're going to do. This is called the geometric sequence. You may have heard of this before. The geometric sequence. This is a specific example type of sequence, although there's not just one geometric sequence. There are, well, they all have a similar format, but this is an important example sequence. And the way that you build this sequence is you choose some real number our book calls it r, that's a lowercase r, to some real number r, and then the sequence is an equals r to the power n. And if you want to write out the terms, it would look like, r squared, r cubed, r to the 4, etc. All right, this is a fairly simple and predictable type of sequence. Depending on what the r is, it has slightly different behaviors. But this kind of sequence arises all the time in real life, because basically what you see here is sort of a sequence which exhibits, I would say, exponential growth. From one step to the next, the exponent increases. And, everybody knows exponential growth is a thing that happens all the time in real life, in biological systems, but also in, growth of economies, even things like growth of people's, like how many YouTube subscribers you have over time. This is also an exponential growth. That's why, like, if you have 10 subscribers, it'll take you forever to get to 15 maybe. But if you have 10,000, it won't take you very long at all to get to 10,005. It's because the amount of subscribers, this is true of all kinds of things in real life. It's true of like bank account balances or something. If you already have a lot of money, it's easy to make a little bit more. If you only have a little, it's hard to make a little bit more. Anyway, all of these kinds of things can be modeled using geometric sequences. That's why they are such an important example of sequences to discuss. And like I said, the behavior of these sequences is different depending on the value of r, the specific value of r that you choose. For certain, I said this is about exponential growth, but actually for certain values of r, the terms of the sequence get smaller every time. Sometimes they get bigger every time, sometimes they get smaller every time. Sometimes they stay the same every time. Can anybody say, actually, is that even possible? Is it possible that these numbers stay the same every time for certain values of r? I think it is possible. Can anybody say a value of r that makes them the same all the time? 1. Yeah, he was giving me the finger. This one, the good one. Yeah, if r is 1, then these values are the same every time. Actually, did anyone have a different answer? Yeah, also if r is 0, these values are the same every time. So I would like to talk, and of course other values of r have other properties, so I want to talk about, depending on what the r is, how can you predict what happens to this sequence? So if r equals 1, then the sequence is just an equals 1, 1, 1, 1, etc., right? So actually this does not grow or shrink, right? Similarly, if r is 0, then it's an equals 0, 0, 0, 0. This also has no growth or shrinkage. Decay is the word that's typically used, the opposite of growth. But if there are other numbers like r equals 2, its an would be 2, 4, 8, 16. These are powers of 2, and of course that increases. Can anybody give me an example value of r where the sequence decreases? That actually is possible. Yeah, somebody said 1/2. If you use 1/2, then it looks like 1/2 and then 1/2 squared, which is 1/4, which is smaller, then 1/8, then 1/16. So this one is increasing, but the one I just wrote is decreasing. All right, so you do get different types of behavior, and you can even get weirder things like, for instance, if r is -1, can anyone say what are the terms of the sequence then? If it's a -1, yeah?
-1, 1, -1, 1.
Yeah, right. This will be, the sequence is always r to the power n. So if it's -1 to the power n, as we all know, this is an oscillating. So this is neither increasing nor decreasing, right? This is oscillating. So there are lots of different options that can happen for different values of r. And I would like to discuss, which is which, like which values of r lead to various different outcomes. Like one very specific question we could ask is, for which r does this sequence an equals r to the n converge? Converge, remember, means that the limit as n goes to infinity exists. Of the ones that I see here, actually many of them do converge, right? Like this one here does converge. These values are just 1 forever, so it converges to 1. This one converges to 0. This one diverges because these numbers get bigger and bigger forever. This one converges. Can anyone say what does this converge to? Converges to 0, right? This one does not converge because it oscillates. So for which values of r, among the ones that I've written, it converges for 1 and 0 and also 1/2. But I want to say, just like in complete generality, can we say for all different possible real numbers, which ones will actually make this one converge? The question really is, for which r does, I'm just rephrasing the same question. Lim n goes to infinity, r to the power n exist. All right? And this question you could try to answer just by like graphing this as a function, right? Remember what we said last time. These limit of a sequence, you might as well think of it as the limit of just r to the power x. And that would be a certain type of exponential function. So make it a function. It looks like, f of x equals r to the power x. And we have talked about this function many times. Usually I write it as like a to the x, but this is just some exponential function that's not necessarily the natural, e to the x, but it's some other thing to the x. And can anybody refresh my memory? What does that graph look like? I remember what e to the x looks like. I hope everybody knows. E to the x looks like this, right? And what are the other, if I change instead of e, use some other value? They look more or less like that again. Like what if, so e is like a little bit more than 2. What if I use 3 to the x? Is it up here or down here? Let me see.
Steeper, like
Yeah, I would say changing the base of the exponent, this e, if I change it to some other number, it just sort of gets steeper or less steeper. So these other bases, they all go through 1 because anything to the power of 0, this is where x equals 0. So anything to the power of 0 equals 1. But otherwise, they are, if you increase the exponent more, they get steeper over here. So these are bigger. Well, can I say over here, these would be curves where r, the base, is bigger than e, where I'm looking at r to the power x, where r is a bigger number than e. E to the x is sort of like the classic one, the OG, if you will. And then on the other side, these steeper ones, they actually go sort of below. And then you could also consider values of r which are less than e, and they go kind of less steep, right? Like so. These are values where the r is less than e. And there is some kind of, if you make the r super duper less than e, you end up with a straight horizontal line. This is the one which occurs when r is, can anybody say? If you continue to decrease the r, now you might think, can I just let the r go all the way to 0? Actually, that would be too far. Any thoughts about this? There's one value of r where you will actually end up with a horizontally constant function. Yeah, this would be r equals 1. Then I'm talking about the function 1 to the power x, which of course is just the constant function 1. So if you continue to decrease the r all the way down to 1, it looks like that. And what if we go less than 1? Can we go even less than 1? Actually, it is allowed. But actually, can I say, first of all, already now we can see on the picture, so by these graphs, we see that this thing, r to the n, diverges when r is greater than 1, right? All of those red curves there, oh, look at that. They're on me. I got to say, like, I have a girlfriend or something to them. I always decline because I don't want to talk to them, but I should probably actually talk to them one of these days. R to the n diverges when r is greater than 1. All right? When r equals 1, it converges. Sorry, I'm stuck. Okay. R to the n diverges. That's because when it's greater than 1, it's one of these curves which goes up forever as we go to the right. But when r equals 1, it converges, although we already knew that. So r to the n converges when r equals 1. And in fact, it converges to the value of 1, right? As you go out to the right on that flat one, its answer is 1, all right? What about the r's being less than 1? So I'm going to try and draw it just because my picture's a little crowded. Let's try and draw values where r is less than 1. So when r is less than 1, that means, like, you know, for example, 1/2 to the power x, right? If I'm thinking about the function r to the power x. So when r is 1, it's that. This is r equals 1. Anyone happen to know what 1/2 to the power x looks like? This is a little strange. Yeah?
The opposite, it goes down.
Yeah, he says it goes down. It looks like this. I think the easiest way to see why that is, or do you have a cute way of seeing?
1/2, it's like the -3 is going to be like 8, and then 1/2 cubed is going to be like 1.
Mm-hmm. Yeah, if you could imagine, if I plug a negative value for x in, say -3, this will say 1/2 to the -3, which means 1 over 1/2 to the 3, which means 2 to the 3. So it's going to be big on that side and small on that side. I think this is similar to what he just said. The way that I think of this is the same as 2 to the minus x. And that means, because that is the same, and what that means is I can think of this as being a horizontal flip of the original graph of these graphs, right? So these ones, when the r is negative, they all look like horizontal flips of these ones. So these ones all look like, I meant to draw it in red, they all look like this. Sorry, it's a little, doesn't look good at all, but that's okay. You know what I mean. They all look like that, all right? So when r is, and actually these also kind of, well, let me say, when r is less than 1, this is only for r greater than 0. When r is 0, you get this special thing where you just get straight 0 all the way across. But I will say for r in this range, it looks like one of those curves up there. R to the n converges, right? Remember, converges means as you go out to the right, these values actually do approach something. And what do they approach on these curves? Yeah?
I have a question.
Yes?
Didn't you just say that r of n converges when r equals 1? So wouldn't you include that in the inequality?
Yes, apart from what I'm about to say right here. Converges to, what did these converge to? 0. Yeah, these curves here are converging to 0. So it's true that it also does converge when r is 1, but it doesn't converge to 0. That's the difference. Yeah. So this is a somewhat strange collection of answers that we're giving here. All right. When r is between 0 and 1, r to the n converges to 0. All right. So what have we covered so far? Up here we covered when r is bigger than 1, it diverges. When r equals 1, it converges to 1. When r is between 0 and 1, it converges to 0. What about when r equals 0? Then it converges to 0 also, right? Because when r equals 0, the sequence just looks like 0 to the power n. So this you could actually include in the statement that I said above. But for r equals 0, r to the n converges to 0. Because the sequence itself is just 0, 0, 0 over and over. And what about for r less than 0? This is the last situation to discuss. For r less than 0, I would say, like for example, like r equals -1. That's my favorite number, less than 0. What does the sequence look like then? R to the n is -1 to the power n. This has alternating signs every time, and so it does not converge. And the same will be true for any negative number that you choose for the r. R to the n will alternate in sign, positive then negative, or I guess it would start negative and then positive and negative and then positive. All right. So for r less than 0, these alternate in sign. And so they diverge. And this is the whole story. We have covered, I mean, there's several parts to this, but we have now discussed all possible values for r and what happens to the sequence. I'm going to try to summarize here, and maybe I'll write this as a theorem. We're not going to write out a detailed proof. It's all based on what I said up there anyway. So the theorem says if r is greater than 1, then r to the n diverges, right? If r equals 1, r to the n converges to 1. This is just a summary of what we said before. If r is between 0 and 1, possibly equaling 0 but not 1, then r to the n converges to 0. And if r is less than 0, then r to the n diverges. And that is the whole story, all right? This I'm not sure I would, well, you should be able to remember this fact. I don't know if you need to memorize it word by word. It's not all that surprising, though, in my opinion. I mean, what you're saying here is if the number you start with is a fraction, it's going to get smaller every time and go to 0. If it's bigger than 1, then it's going to get bigger every time and basically go to infinity. And it's not hard to remember. If it straight up equals 1, you just get 1. And if it's negative, then it also oscillates so that it diverges.
Can you just say the absolute value of r diverges if it's greater than 1?
Yeah, you can say that. So these two situations are actually a little bit different. So if you want to be technical about it, you can say in the first case, r to the n diverges to infinity, meaning that these terms grow larger every time. And so that is one sense in which this first case is different from the last case, because the last one is diverging because of oscillations, not because it grows forever. Although if all you care about is converge versus diverge, you can just say that it's about absolute values. Although even so, like if the absolute value of r equals 1, you still don't know if it converges or diverges. So you will see if you look in textbooks, you'll see versions of this written in terms of absolute values, but this is the way that our book likes to write it, which I think is fine. All right. This is everything you could want to know about the geometric sequence. All right, let's talk about one more thing from this section. I would like to talk about increasing versus decreasing sequences. Increasing versus decreasing sequences. What I mean by increasing would mean sort of when you look at a graph of the sequence, I mean like it goes sort of up every time, right? And decreasing would mean the dots go down every time. Let's write a real definition here. The sequence an is called increasing. When, anybody think you can say, how do you say this technically speaking? Each one, it goes up. Anyone want to try and say this in a sensible way? Don't say it goes up. Yeah?
A n plus 1 is greater than a n.
Yeah, I like that. A n plus 1 is greater than a n, I will say, for each n. Yeah, excellent. This is the definition of an increasing sequence. It means sort of no matter where you're looking in the sequence, the next one is always bigger than the previous one. That's what increasing means. And then decreasing is the opposite of that. So it's exactly the same, but it has the inequality going the other way around. So decreasing when a n plus 1 is less than a n for each n. That is a decreasing sequence. It means the next one, no matter where you're looking in the sequence, the next one is always less than the previous one. This is how you define increasing and decreasing. And there's one more word that comes up often. A sequence, this is a somewhat fancy word, is called monotone. Monotone in ordinary language, when somebody says like, that guy's voice is so monotone, that kind of means like it's just doing the same thing over and over again. That's what the word monotone in common parlance means. A sequence is monotone when it is always doing the same thing. That is to say, it's always either increasing or always decreasing. So a sequence is monotone when it is either increasing or decreasing. And of course, many sequences are neither. Many sequences, they go up sometimes and sometimes they go down. So that sequence would not be increasing or decreasing. It is not monotone. When I tell you a sequence is monotone, it just means either it's increasing or it's decreasing. It may be surprising that such a word is actually useful for anything, but it is. There are many things that are true of any monotone sequence, whether it's increasing or decreasing. There are theorems about monotone sequences. All right, let's try and do a little business with this increasing or decreasing. So this is something that you may see in like homework problems. Here is an example. Show this sequence is increasing. How about 3n over n plus 1 is increasing? All right, let's try it. What it means, according to the definition. Now, I should say, you might think that this would have something to do with derivatives, because if I ask you to show me that a function is increasing, that means the derivative is positive. But actually, that is not the definition of increasing for a sequence. The definition of increasing is this right here. So this is what we need to demonstrate. So we need to show that an plus 1 is greater than an, right? So now, when you are writing down, this is not really very hard to do, but when you're writing down your answer, I would like for it to be sensible. And one way in which people write these badly, sorry, I'm trying to fix my W. One way in which people write these badly is by making a bunch of confusing things where I can't tell the difference between, are you telling me what you want to show, or are you actually showing me something? So here's how I would write this. We need to show that that is true. So another way of saying that is, I'm just going to write each of those two things and try to simplify as much as possible. An plus 1 versus an. Maybe I'll do the an first just because that's a little easier. An is 3n over n plus 1, right? What is an plus 1? that means you go back up to the original formula, but you replace n with n plus 1. So it's going to say 3n plus 1 divided by n plus 1 plus 1, right? And what is that? I will try and simplify this. You can distribute the 3 on top and then add up the 1s on the bottom. So this says 3n plus 3 divided by n plus 2. All right. And so what we need then, now when you're writing this down, I think you must write some words. I don't know if you are a words hater. I have encountered many calculus students who's like, the worst thing possible is to write a word in English. I don't know why people have this attitude, but if you read real mathematics, it is written in words. So you should write some kind of words. You don't have to write exactly the words that I write, but we need to show that 3n over, I'm trying to write just what I said at the top, right? an plus 1, so I'm going to write 3n plus 3 over n plus 2 is greater than 3n over n plus 1, right? This is what we need to show. Would anyone like to suggest how to show that? You want to do something, yeah?
Can you just plug in any value, like 1 or greater, into n, and then see what it equals?
This is not a bad idea, but not a good way to prove. You have to prove that this is true for all values of n. So it's not good enough if you just say use n equals 1 and see what happens, because then you will have only demonstrated for just one value of n. Yeah?
Do you set the limit to like infinity?
I was not going to do that. This actually, nothing here is about limits. So I'm not trying to show that they have the same limit. I'm trying to show individually this fraction is always bigger than this fraction. Yeah?
Find a common denominator and then multiply it out and see which is larger.
This is not a bad idea. I think actually a common denominator is not really necessary here.
Or like multiply the n plus 1 times the n plus 3 and then n plus 2 times the
Yeah. So I would, right here, imagine like you're trying to solve for n, even though we're not going to solve for n, but just to simplify this, I would sort of multiply the denominators across here. So we need to show this, and I will say this is the same as, I'm going to simplify, and you can simplify however you like, and to me, how I like is I'm going to multiply those denominators across. So this will say 3n plus 3 times n plus 1. I think this is what she was getting at. 3n times n plus 2, like that, right? Anybody feel nervous doing that with an inequality sign? Are you allowed to do that with an inequality sign there? Certainly, if it was an equal sign, you could do that. I see some nodding people. This is usually what happens if I ask a calculus student, are you allowed to do that? Oh yeah, sure. No problem.
Switch it?
Yeah, you should think about, should I be switching the inequality sign or something like that? Everyone knows the first rule of Fight Club is that when you multiply both sides by a negative number, you have to change the inequality direction. Did we just multiply both sides by a negative number? No. And why not? It's because the n is positive. So actually, this step, usually you should be concerned about, do I need to change this around? But because I'm talking about sequences and the n's are always positive, that means n plus 1 is always positive, n plus 2 is always positive. And so this operation does not change the direction. So maybe if you wanted to justify this, I would just say n plus 2 and n plus 1 are positive, which means you don't have to worry about the changing the inequality sign. But you should, on some level, you should think about that. Anyway, this is now the same as 3n plus, so I'm going to actually distribute these out. It'll say 3n squared, I'm doing the FOIL, right? Plus 6n plus 1 is greater than 3n squared plus 6n. All right? So this is also, I'm going to put a few more words here. It's the same as that. Eventually, hopefully, we will simplify it so much that it becomes obvious. Is it obvious yet that the thing on the left is bigger than the thing on the right? I think it is at this point obvious that the thing on the left really is bigger than the thing on the right. If you're still not convinced, you can just subtract 3n. I wrote 3n to the n. Sorry, that should be n squared. That don't make no sense. This is the same as remember, all of these same ases is part of a we need to show, all right? So we need to show, I could even subtract the 3n squared from both sides and the 6n's. 1 greater than 0 is all that's left over, which is obvious. This is how the proof ends. Schön. All right? The end. Did I mess something up?
Yeah.
I think it's 3 instead of 1.
3, not 1.
Yes, you're right. Sorry about that. Thank you. 3, not 1 on the left. It don't change the final step. Any other objections? All right, you are right to object. Okay, so this is how the proof ends. Can I just say, here's what I don't want you to write. I don't want you to write this. an plus 1 greater than an. And then over here you say 3n plus, whatever I said before. 3n over n plus 1, right? And then you go 3n plus 3n plus 1 greater than 3n n plus 2. And then you distribute and subtract. You end up with 3 greater than 0. And then you're like, yes, 3 greater than 0. I have proved it. This is for the haters of writing words. Just this is a bogus proof. Really what you mean is, because when you write it in this way, it seems like you're making a logical argument where you start with this, from which you get this, then I get this, then I get this, and I'm done. It looks to me like you have just proved that 3 is greater than 0, which I already know, and anyway, you didn't prove it. Really, the whole argument, in terms of a logical argument, is actually backwards here. What you need to show is this. That is equivalent to this, and this, and this. And so what you need to show is the same as this obvious fact. That's how you have to write it. So you don't have to say exactly all of these words that I said, but you have to somehow indicate the flow of the logic, which is actually somehow reverse from the way that this is written. All right? So I have one for you all to try. I'm not going to be super picky about how precisely you're writing these arguments, but as far as I can tell, you must use some real words, unless you write literally these steps backwards, which you would never actually do. So how about try this one? Show that n over n squared plus 1 is decreasing. This one, if you do it similarly, you will get down to some kind of ending step similar to this, although when you do it, the last part is, I would say, less obvious than 3 greater than 0, but still obvious. So you might have to say a few words at the very end also. See how it goes. does simplify a little bit. You know?
Yeah, take out the end.
Taking stuff out.
I went back to
Well, I would say subtract a little. And keep on both sides. Keep subtracting. Yeah, that's making sense. All right. Yes, I think so. Continue simplifying by like canceling stuff out. Move everything to one side if you like, or something like that. Move it here. Yeah, like that. So there's a this is simplification. Because this is only a factor in one and not this. So you have to do the FOIL and then add it as a section. It's quite different.
Is this like enough for the final score?
Yeah, I like that.
That's what I'm like asking. It's just like a complete first, but you have to say
I'm the only person in the world who plays money. Can we discuss? I see some people have gotten to the end. It's a little tricky about what exactly you should say at the very end. Is a little maybe not obvious, but we can talk about it. Okay, so here's my little proof, I suppose. You can write the P word if you want. So I need to show, here's a little shorthand. Often I will write WTS. This means I want to show. This is for the haters who don't like writing words. Do you prefer writing WTS? I don't know. I want to show that AN plus 1 is less than AN, right? This is the same as I want to show that N plus 1, so here I'm just putting in the plus 1s everywhere, is less than N over N squared plus 1, right? And now I can simplify that. I'll just put this WTS in the front every time. Isn't that cute? N squared plus 2N plus 1 plus 1. I hope I'm doing okay so far. And then the thing on the left, I suppose you could add up the ones in the bottom. This is the same as N plus 1 over N squared plus 2N plus 2 less than N over N squared plus 1. And now we can do multiply the denominators across, just like we did in the previous example. So I want to show all of this is still equivalent to, now it's this less than N squared plus 2N plus 2. I hope everybody is doing more or less the same steps so far. I haven't really stopped to think much. It's just a bunch of simplifying step by step. What did you do next? I know many of you worked this all out. What did you do next? Did you do anything next? No? Yeah, keep on simplifying. So we can do the FOIL on the left, and then on the right, multiply across, distribute the n. So on the left, it's going to be n cubed plus n squared plus n plus 1, I think. And then here, n cubed plus 2n squared plus 2n. All right, what next? I saw a lot of people kind of stalled at this point. Can we continue to simplify? This is what I want to show. Yes? What else? What do you say? He's nodding.
Subtracting to get n squared besides.
Yeah, on either side, I can just like subtract n cubed from both sides. Like these guys can be subtracted, and then furthermore, I could subtract n squared on both sides, and one of the n's also. This is the same as n. No, on the left, I can just end up with 1, right? Less than, and on the right, n squared plus n, right? And I want to show that. And here you can't simplify anymore. In the previous example, at this step, we got something like 3 is greater than 0, and I just said this is obvious now. This is a little less obvious, I suppose, but what did you say to explain this? Why is this true? This you just have to explain straight up why that is always true. Anybody say something?
N is greater than or equal to 1, so.
Right. This is a sequence, so n is greater than or equal to 1. And that thing on the right-hand side, if n is at least 1, then it's always going to be bigger than 1. All right. So this requires some amount of argument at the very end, but you can say it's something like this. Since n is greater than or equal to 1, we do have 1 less than n squared plus n. Because this thing over here is at least 2, right? If n is bigger than 1, greater or equal to 1, the right side of that inequality is at least 2. So in this case, you do need to say something like that at the very end. But it's not very complicated, all right? I hope you agree with that. This is how you show that a sequence is increasing or decreasing. Arguments like this. Usually there's not much to it. It's just, it may take a bit of getting used to exactly how you write down the steps. All right? Excellent. What about to show that a sequence is not increasing or not decreasing? That's actually easier. So to show a sequence is not increasing or not decreasing. These are not opposites of one another, by the way. Like, not increasing does not mean that it's decreasing. Not increasing means that it just doesn't get bigger every time. It means sometimes it gets smaller, but it doesn't mean it always gets smaller. Anyway, to show that a sequence is not increasing or not decreasing is easier. Let's just try an example like that. Show that, how about an equals minus n to the n. How do you like that? I really do mean this one now. I wrote n to the n before as a typo, but this is not a typo. Show that this is not monotone. Sometimes they use this as an adjective. They would say monotonic. It is not monotone. What that means, remember, this means not increasing or decreasing. And for this, actually, all you need to do in this case is plug in specific values. If it's increasing, it means it gets bigger every time. To show that it's not increasing, all you have to demonstrate is that at least sometime it doesn't get bigger. So for this, I said this is easier. It's because all we need to do is write out the terms. And I might as well just like start with n equals 1, right? So here, an equals the first term, minus 1 to the 1, minus 2 to the 2, minus 3 to the 3, minus 4 to the 4, etc., right? And if I were to, calculate those out, this is negative 1. This is 4, because it's negative 2 squared is 4. Negative 3 cubed is negative 27. Negative 4 to the 4, I believe 4 to the 4 is 64. So this would be positive 64, etc. All right? And then, can you explain why this sequence is not increasing and also not decreasing? I would say it's not increasing because right there it decreases. All right, so this is not increasing since, in particular, I can say since A3 is less than A2, right? A3 would be negative 27, A2 would be 4.
4 to the 4 is 256.
256?
Yeah.
16 times 16. Yeah, okay. Yes, I agree. Thank you. 256. This is my mental calculation. My mental calculation game is not good. Anyway, this does not contradict what I was saying. Since this term is less than that term, it means it's not increasing because right there it decreased. And why is it not decreasing? Because right there it increased, right? The fact is sometimes it increases and sometimes it decreases, which means it is not an increasing sequence and also not a decreasing sequence. So it's not decreasing since A, in this case, A2 is greater than A1, all right? So this sequence, sometimes it increases, sometimes it decreases. Which means overall it is not an increasing sequence, and it's also not a decreasing sequence. So it is not monotone. All right? That's easier just because all you got to do is write down a few numbers and see that sometimes they get bigger, sometimes they get smaller. All right? A couple more simple bits of terminology. And I got one important theorem, which I think we can say. We're not going to try and do a big proof of it, but I think we can say at least before we leave today. One last bit of terminology is bounded sequences. This means what you think it means. A bounded sequence is one which does not go up to infinity. So bounded means all the values are less than a certain sort of upper bound, as we say. So a sequence is bounded. It means the values of the sequence never go up past a certain amount. And that certain amount is called the upper bound. So I'm going to say a sequence is bounded if there is some upper bound, which is a number that the sequence never goes above. And that number, so in our book, it is called M, big M. I imagine M means something like maximum or something. There's some upper bound M such that AN is less than the big M for every N. All right. Bounded means there is an upper bound, and the terms of the sequence never go past the upper bound. They are always less than the upper bound. This is probably what you thought I was going to say if you thought about it for a while. This is what it means to be bounded. And the picture you should have in mind is something like a sequence like this. Maybe it goes up, but it doesn't go up past a certain amount. And M is just some number up here, which is always greater. That Y value is M. And here, this sequence is bounded. The language that is used, sometimes people say bounded above by M. There is some kind of ceiling that the values of the sequence never exceed that number, big M. This is called being bounded above. Or there's also such a thing as bounded below. Now, when people say the word bounded, it means this, bounded above, but to be more specific, often, and our book often writes it this way, sorry to squeeze this in, bounded above, just to be clear, because they're also going to talk about bounded below, so it means all the same stuff, only bounded below means there's a number sort of down at the bottom that they never go down past. So a sequence is bounded below when there is some number, the lower bound. There is a lower bound. I hope you don't mind, but our book calls the lower bound little m, which means, I guess, minimum or something. Big M is what they call the upper bound. Little m is what they call the lower bound. So bounded below when there is a lower bound, little m, such that a to the n, or an, the sequence term, is always bigger than the lower bound for all n. All right. That's called bounded below. And the picture you should have in mind for this is similar. It would be the terms of my sequence never go down below a certain amount. This is the lower bound for those terms. All right. It means there's a number that the terms never go down below. That number is not unique. That is to say, this is a number where the terms never go below here. Of course, you know, this down here is also a number where the terms, they never go down below that either. So there's not such a thing as the lower bound. If you have a lower bound, there are many more lower bounds, even lower than that. But we generally talk about, well, it just means that there is a lower bound. There's not necessarily just one lower bound for the sequence. All right, so we got plenty of time here. I know it's getting late, but I got to use the time allotted. Let's see if we can demonstrate this. So here's another typical, homework problem about bounded sequences. Show that n over n squared plus 1 is bounded above and below. All right. Your job will be to tell me what some upper bound and lower bound for these guys is. I would say if you don't know anything about how you're going to demonstrate this, I would suggest try to calculate some of the values to get a feel for what these values look like. So this is not really part of my argument, but just to get a feel for things, you could plug some values. The terms look like 1 over 1 squared plus 1, 2 over 2 squared plus 1. Maybe I'll just write the first 3. You can do more if you really want. This is 1/2. This is 2/5. This is 3 over 10, etc. Just writing it like that, don't really have a great feel for what the pattern is, but 2/5 is a little bit less than 1/2, right? Because 1/2 in terms of fifths would be 2.5 fifths, and then 3/10 is a little bit less even than that. Anyway, can anyone, so your job here is to show that it's bounded above and below. Let's talk about below first of all. Can you think of a number that is going to be less than all of these terms? These are really two separate steps. Let's talk about bounded below just because I happen to know that's a little easier in this example. So for this one, we need a specific number. We need some little m so that little m is less than n over n squared plus 1, right? The lower bound should be less than all the terms in the sequence. Any ideas? The m can be any number which you know is always going to be less than these guys. I have one number in mind. Maybe somebody else? I see some usual suspects offering the answers. I appreciate the usual suspects. Someone I haven't heard from? I see somebody showing me the fingers, but I don't think it's intentional. I think it's the natural positioning of your hand at this moment. Any ideas? A number which is less than all of these things. One of my personal favorite numbers I have in mind. I see somebody's hand in this position. That's because they're looking at their watch. But actually the fingers are showing me my favorite number. The answer is 0. That's what I'm looking for. All of these are bigger than 0, aren't they? I think they are. Now, certainly they look bigger than 0. Can anybody explain, actually? Let's use m equals 0. So I want to show that n over n squared plus 1 is always bigger than 0, right? Is that true? Bigger than 0, of course, just means it's a positive number. Yeah?
Yeah, because of the plus 1 in the denominator.
Because of the plus 1 in the denominator?
Because it could never. I mean, you can have 0 over some. Oh, I guess never mind.
I think it's a little simpler than whatever she was thinking. You got an idea?
Since n is greater than or equal to 1, it'll always be positive.
Yeah, this fraction here must be a positive number just because n is positive, right? Nothing here could possibly be negative because n is 1 or more. I will just say this is true because n is positive, right? And I suppose, I mean, the fact that it's plus 1 in the bottom means the bottom is still going to be positive. If this said something like n squared minus 10, then I would be concerned that the bottom could be negative sometimes. But it doesn't say that. It says n squared plus 1, which means it's positive. All right, and what about an upper bound? Can anybody think of an upper bound? This is a little bit trickier, but when I look at these fractions, I notice the denominator is always bigger than the numerator, and this suggests to me a certain upper bound. Any ideas? So how about bounded above? Yeah?
If the denominator is greater than the numerator, it has to be less than 1.
It has to be less than 1, right. These are always fractions where the denominator is bigger than the numerator, and so these fractions must all be less than 1. So here we can use the big M is 1, and n divided by n squared plus 1 is always greater than 1 because n is smaller than n squared plus 1. So the denominator is the numerator is less than the denominator. The number less than the denom, all right? And so that means the value of the fraction is less than 1. So this is bounded below and also bounded above. These you may have to get used to sort of, these can be a little tricky just because I am more or less coming up with these two numbers out of nowhere. And you have to kind of get used to the way that these problems typically go.
Maybe
Yeah.
the sign the other way.
The sign the other way? Here?
No, for n
N over n squared plus 1 is less.
Less than 1 is what I meant. Yeah, thank you. Sorry. I'm extra tired today. This is a true story. I'm feeling very tired today. The only reason I can think of is because I know that I have to stay up late tonight. Does this happen to anybody else? I didn't stay up late last night. Makes me feel tired to know that I have to stay up late tonight. It's a true story. All right. One last thing to say. What does this all have to do with converging? All right. So bounded above and below versus converging. They are similar concepts, but not the same. Like, for example, in this case, this sequence here is bounded above, and at least the way that I drew it, it converges to this value, big M, right? And so it seems to me like you might want to say a general statement like, if it's bounded above by M, then it converges to M, all right? This is not quite true, though. That what I just said is not quite true. So there is a relationship, though, between boundedness versus convergence. They are similar, but not exactly the same. So, for example, in this, I'm just going to draw a similar picture to that one again. If I have some kind of upper bound like this, I'll call it M, and the sequence goes up to m like that. So here, it's bounded by m and converges to m, right? But that's not always the case. Can anyone imagine a sequence which is bounded by m but converges to something else? Is that possible? Could it be bounded by m but converge to something other than m? Like here, it's bounded there and it converges to there. Yeah?
1 over n.
1 over n. Yeah, like what if the dots, they just like go down instead of up, right? Like just the fact that it's bounded by m does not mean the dots actually go up to that point. It just means that all the dots are below the line. And they could converge to anything below the line then. So it's bounded by m and converges to m in that picture. But that is not necessary. So it could be that it's bounded up here by m. Like here's m. But then the dots, all that means is the dots stay below the line, right? It doesn't mean that they go up to the line. It just means they stay below the line. All right, so here it's bounded by m, but converges elsewhere. It doesn't converge to m, it converges to something else. Does it even need to converge at all? I think it doesn't. Actually, you could do one of these like alternating things. As long as it's under the line, it's still bounded. But that doesn't mean anything about if it converges or not. So here's an example of a bounded. Bounded just means it's under the line. All the terms are below the line. But the terms themselves, they could go something like this, right? -1 to the n. This is bounded, but doesn't converge at all. This suggests that there's really no relationship at all between boundedness and convergence, right? It can be bounded and converge to the bound. It could converge to something else, or it can converge to nothing at all. So the concept of boundedness and convergence are not easily related. There is a relationship, though. Maybe we will start off next time talking